So I'm going to talk about emergence from anesthesia before I start to talk about coasting, because it has a lot to do with it. So how do we wake up patients from an anesthetic? We always talk about induction, the start, and the maintenance, but we almost never talk about emergence from anesthesia. So how do we wake up our patients? Well, first of all, we stop the administration of the anesthetic. So we turn off the vaporizer, and we increase fresh gas flow so that it is higher than minute ventilation, and hopefully there is no rebreathing at that point. In general, there is no or very little rebreathing. So this is how we wake up patients, and then we let the lungs clear or inhaled anesthetic. So the clearance can be calculated by the amount that is transferred towards the lung with venous blood, by the amount that is exhaled through the alveoli, divided by the amount that is transferred to the alveoli with mixed venous blood. That is clearance. It's the same thing for renal clearance, the same thing for hepatic clearance. That means that if we look at the individual parameters of the amount that's exhaled, we know that minute ventilation plays a role there. In other words, if we increase minute ventilation, you can expect patients to wake up faster. And actually, that works. Because if you do isocapnic hyperventilation, you have to add some CO2 so that you maintain cerebral perfusion. If you do isocapnic hyperventilation, patients will wake up faster. It also has to do with blood gas solubility. And blood gas solubility is very important. Because if you look at this simple example, if we have a state where we have particles or vapor in blood dissolved, and you expose it to a gas phase, if the blood gas partition coefficient is 2, then 6 of the vapor molecules will stay in the liquid phase, and 3 goes to the gas state. If you do that with a blood gas partition coefficient of 0.5, then it's the opposite. 6 parts of the vapor will go to the gas phase, and 3 will remain in blood. It's clear from just looking at it that a gas with a low blood gas partition coefficient will be cleared much better. If we look at venous return, the venous return depends on the tissue gas solubility and on the duration of anesthetic, on how much of our containers have been filled up. And this is a hydraulic illustration of the 4-compartment model. Anybody who has read Low and Ernst knows what this means. And I have 4 different compartments. I have the inspired reservoir, which is not really realistic here, but we have alveolar gas, or FA. We have the vessel-rich group, which includes the CNS. We have the muscle group, and we have the fat group. And during our anesthetic, these containers will gradually get filled up. And the ones with a lower time constant, which means smaller capacity and higher perfusion, will get filled up faster. Now, if you really have a long anesthetic, then especially the muscle group will be filled up quite a bit. And that vapor in the muscle group will then gradually get released at the end of the anesthetic when your patient wakes up. So it's obvious that the size of these containers and the degree to which they are filled plays a role in the awakening process. So what plays a role here is the capacity, the size of the organ, and the solubility of vapor in the organ tissue. That tells you exactly how much of the vapor will end up in the organ at time infinite. And we know the agent transport, which is organ perfusion and depends on blood solubility. So if you divide these two, then you get the time constant. Although time constant usually is determined by volume over flow, in this particular situation, it is capacity over agent transport. And we know that after 3 time constants, you have 95% equilibration. So anyhow, if we look at the duration of the anesthetic as an influence on emergence, on the amount of vapor that returns to the lungs with venous blood, then for a very short anesthetic, 5 minutes here, very little, in this case desflurane, has been transferred to the muscle group, because it takes a while for the muscle group to fill up. So if you turn off the anesthetic at the end, there is not a whole lot of vapor that will return to the lungs from that muscle group. Notice that the vessel-rich group is quite small, so that that will get eliminated and cleared and exhaled very rapidly. If you look at the right-hand side for a long anesthetic, then we see that this container, the muscle group especially, is filled up quite a bit more. So there is more vapor for a longer time coming back with venous blood that has to be cleared before your patient can wake up. In other words, wake-up time depends on your duration of anesthetic. With longer anesthetic, muscle group is more saturated. The time constant for the muscle group of desflurane is 95 minutes, for sevoflurane is 148 minutes. So it takes longer for that muscle group to fill up with sevoflurane. However, the total amount of sevoflurane that is in there is quite significantly higher. Therefore, if we compare the situation with isoflurane versus sevoflurane, the effect of the tissue group is that, yes, the muscle group here is saturated quite a bit higher with desflurane as compared to isoflurane because the time constant is different. What we see is that the total amount of vapor that can be returned from this container with venous blood is quite a bit larger, and that will slow up recovery from the anesthetic. So I had to go through the example of emergence from anesthesia before I can start with the principle of coasting, because coasting is actually doing the opposite of waking the patient up. Now with coasting, we're trying to prolong the anesthetic a bit longer with very low fresh gas flows or closed circuit anesthesia without adding any further anesthetic. So therefore you have to understand the principle of clearance, and that's why I had to go through my first 5 minutes of my presentation. If you look at the definition of coasting in Wikipedia, I think the best description is the first one: the performance of a natural deceleration of a motor when the power is removed. In other words, in anesthesia practice, we just recycle the gases within the body. Nothing gets exhaled. In other words, our motor is turned off. How long do we last? How far can we go with the motor turned off? That's what actually Lowe and Ernst determined when they talked about coasting. So anesthesia can be maintained for a while near the end of closed circuit anesthesia while you have the vaporizer turned off. Why does coasting work? Well, because all the exhaled gas is re-inhaled, the clearance is zero. So you don't lose any of your vapor through exhalation. Secondly, the partial pressure in your vessel ridge group, and therefore your CNS, will decrease gradually due to redistribution from the vessel ridge group to the muscle group. There's probably also a bit of redistribution to the fat group, but usually in these kind of kinetics we ignore the fat group. And there's a little bit of metabolism, also very small. And the goal now is to maintain the partial pressure in the CNS long enough so that we can maintain the state of unconsciousness in our patient. So we all know the 4-compartment model of Eager. And what coasting means is that we eliminate the clearance through the lungs, and some of the vapor that was in our vessel ridge group will get redistributed to the muscle group, because most of the time the muscle group is not quite as saturated as the vessel ridge group. Therefore, its partial pressure is lower, and our vapor or anesthetic gases move according to partial pressure gradients. So if we look at the hydraulic model, then coasting means that we lose no gas through ventilation, and some of our vapor will be redistributed from the vessel ridge group to the muscle group, because the partial pressure, which is suggested by the height of the column in there, is larger in the muscle group. So we're going to have some vapor go from vessel ridge group to muscle group. So Lowe and Ernst, in their classical book, described or defined coasting as the time for the alveolar pressure, partial pressure, to drop from 0.65 to 0.35 Mach. That's a 46% decrement time, and that was their definition of coasting. It is usually done in combination with nitrous oxide administration. And then when you open the circuit and you wash out nitrous oxide, high fresh gas flows, nitrous oxide will be washed out very quickly, And the goal is that when your potent inhaled anesthetic is at 0.35 MAC, it doesn't take a long time for your patients to wake up, because now obviously you're clearing the agent through the lungs. However, I felt that the quantitative aspects of coasting were poorly described by Low and Eager. They didn't give a lot of examples, and they suggested that coasting time was 2 times the square root of the anesthesia time plus 1. In other words, the coasting time would get longer with a longer duration of the anesthetic. But then they claimed also that the formula was only valid for anesthetic durations of 1 to 4 hours. For short anesthetic, the formula overestimates the coasting time. For longer anesthetics, it underestimates the coasting time, what is described here. So if you have an anesthetic of 16 minutes, the square root of that is 4. 2 times 4 is 8. So the coasting time should be 9 minutes. And it's actually quite a bit shorter. So they said that the formula overestimates the true coasting time because the lines here are patient observations. You will notice that there are no standard deviations in these patients' observations. It has never mentioned how many patients they actually study. So this is kind of a black box. So my conclusion from Low and Ernst is that they gave us a poor description of the kinetics of what happens during coasting, and they provided little or no information regarding the agent solubility. Now, you could say, well, let's look at some other clinical studies, but there are virtually no other studies done. Except, of course, that Jan did some studies on that many years ago, more than 15 years ago, and this was presented in 3 abstracts in those years. So, and we determined clinically in patients the coasting time with isoflurane and desflurane, and for different durations of the anesthetic, for 4 minutes to 100 minutes, for both iso and des. And we found that the coasting time, or described here as the 48% decrement time from 0.78 to 0.41, was about 5 minutes for the 4-minute duration of anesthetic, and for the longer duration of anesthetic, 100 minutes, was just under 20 minutes. What we saw that was the coasting time was slightly longer with a lower soluble agent. So you could coast longer with a less soluble agent. When we looked at more of the individual data, you can see that the standard deviations are quite large. And also for the desflurane, the coasting time seems to have leveled up over time. I think someday we should repeat all these studies and try to be a bit more accurate. But still, the conclusion that we can make from the previous data is that the duration of anesthesia influenced the coasting time. Coasting time is longer after longer anesthetics, and coasting time is longer with less soluble agents. I think we can conclude that from that study. So how can we verify this if we don't have any other patient data? I did a Gasman simulation. I think everybody knows Gasman. If you don't Gasman, just enter it in Google and you will get there. So Gasman simulation is a computer model that works according to the uptake model by Eager, with some modifications that are proprietary, I think. Not anymore? No. Okay. So what did I do in the simulation with Gasman? I gave an anesthetic, general anesthetic with isoflurane and desflurane, at 0.65 MAC, and that gives us 0.78% of iso and des 3.9%. So that was the maintenance anesthetic. I did that for 2 different durations, for 30-minute anesthetic and for 3-hour anesthetic. So this simulation, consisting of 4 parts, allows me to determine the effect of duration of the anesthetic on coasting time and the agent solubility, the effect of solubility on coasting time. So I looked for the 46% decrement time, which means 0.65 to 0.35 MAC, as classically described by Low and Ernst. That means that my target concentration was 0.42 for iso, and for des it was 2.1%. And I found that the coasting times were indeed what we thought they would be. A little bit more simplified, 9 minutes for ISO short anesthetic. For long anesthetic, 17 minutes. In other words, duration of anesthesia increases coasting time. When you look, same is true for desflurane. When you compare ISO and desflurane, coasting time increases with lower solubility. To give you the example or more concrete idea of what we did, this is the 30-minute desflurane coasting. We kept concentration quite nicely constant, alveolar concentration at 3.9%. After 30 minutes, we saw that the vessel-rich group was virtually 100% saturation, and the muscle group was just under 30% saturated. Then we turned off the vaporizer. We closed our circuit. We went to 150 mL per minute fresh gas flow, virtually closing the circuit. And then we waited until the concentration in the alveoli was 2.1%. And that defined our coasting time. And we measured 14.53 minutes. So that's how we did that. For desflurane, very similar. After half an hour, we had to wait 14.5 minutes for the alveolar concentration to decrease to 2.1%. If we look again at the ISO 30-minute coasting time, this is where we got the numbers. At 39 minutes, we went down to a concentration of 0.42%. So that was our coasting time for ISO after 13 minutes, or 30 minutes. Note that we still have quite a higher concentration in the vessel-rich group as compared to the muscle group. In other words, there was still agent at that time going from vessel-rich group to the muscle group. So my idea was, well, this is indeed how it works. Coasting means that you stop clearance and you have vapor going from the vessel-rich group to the muscle group because of the differences in partial pressure there. But then I looked at the 3-hour coasting times a little bit more in detail, and here you see that we have the steady state at 3 hours. That's when we turned off the vaporizer, and we saw that 25 minutes, 56 seconds later, we reached our target concentration. What's remarkable here is that the partial pressure in the vessel-rich group was now lower than the partial pressure in the muscle group. So my first hypothesis that the vapor is going from the vessel-rich group to the muscle group during coasting was not completely correct, because at this point there cannot be vapor going from vessel-rich group to muscle group. It's impossible because the partial pressures are too different. So therefore I have to conclude that yes, during some part of the coasting it's clear that vapor moves from vessel-rich group to muscle group, but there also has to be a time during coasting that the vapor moves from vessel-rich group to the fat group. There is no other tissue group that can contribute to coasting than the fat group. So fat has to be involved in the coasting process. So my conclusion from these Gasman simulations now are that indeed coasting time increases with longer anesthetics and lower solubility, but the kinetics have been poorly described. Besides redistribution from vessel-rich group to muscle group, there is also redistribution to the fat group. And we may say, well, coasting, we shouldn't do that because we don't understand how it works. But in clinical practice, it just works. We don't know all the details. It has to be further studied, I think. But if you do it, it just works. So you turn off the vaporizer way before the end of the case, which results in a further small reduction in cost besides using low flow to start with. But there's another advantage there. There is less hysteresis. With slow alveolar washout, the FA represents FVRG much better. And that was confirmed in our Gasman simulation. So if we looked at this simulation here after 25 minutes, we saw that the alveolar partial pressure was just slightly lower than the vessel-rich partial pressure. So at the end of coasting, our alveolar partial pressure very closely reflected vessel ridge group and therefore CNS partial pressure of the agent. And therefore the MACAWAKE principle works much better when you have this more gradual washout of your agent as compared to when you have your fast washout of agent. There is virtually no difference between the two partial pressures. So the key elements of coasting are let the vessel ridge group potent inhaled anesthetic decrease to about 0.35 MAC, which is what we do with coasting. Maintain your general anesthetic by the use of nitric oxide, about 0.65 MAC. The potent inhaled anesthetic plus the nitrous oxide plus the proper dose of opioids for post-op pain relief should result in achieving all your goals of general anesthesia, which are unconsciousness, immobility, and hemodynamic stability. So your patient is perfectly stable and fine during coasting, even at the end of coasting. When you want to wake the patient up, you turn off your nitrous oxide, increase your fresh gas flow that there is no rebreathing. The nitrous oxide will be washed out very rapidly from your vessel ridge group, typically about 2 minutes. Your total MAC will be now lower than 0.35 MAC. And as I said, your partial pressure in the brain for your potent inhaled anesthetic is very close to the partial pressure in the alveoli. So this MACAWAKE principle works much better. And you have a very rapid, predictable emergence. If you at the same time don't harass your patient by shaking them or putting a Yankauer in their mouth, they will wake up very smooth. They just wake up, they follow commands, they open their eyes. If they're breathing, you take the tube out. Very simple. Coasting can be made even easier than what I just presented because technology is going to help us. Technology consists of a couple examples. For example, this is the flow-eye, where we have a predictive display indicating what is going to happen over the next 20 minutes or so. We also have the Smart Pilot prediction tool, and there the Smart Pilot will tell us, if you don't change anything else, what's going to happen 10 and 15 minutes from now. So we're going to have technology helping us in this coasting process and make it even easier for us to use. So my conclusion is coasting, although we don't understand the kinetics, it just works. It's very easy to follow, so just do it. Thank you.